Hi, my name is Will Krawczyk, Scientific Services Manager at Chemical Computing Group. Today I'd like to demonstrate the fragment-based drug design tools that we have in Mo. In today's session we're going to be taking separate fragments that occupy different parts of the same pocket, and then we'll search for a linker so that we can create a single small molecule ligand. A typical starting point for this workflow would be the results of a fragment screen or perhaps crystallographic fragments. So let's get started. So I'll use the Open button to retrieve the file that we're going to be working on today from the sample mol directory. The file is 1kv2. I select it in the Open panel, click OK, and I'm greeted with this Load PDB panel, which allows me to select what data we're going to load into Mo. Here I'll accept the defaults and we see the structure appear on screen. This is human P38 MAP kinase, and you'll notice that it's coloured by its secondary structure. So we've got beta sheets in yellow, helices in red and turns in blue. Now before we can start thinking about fragment-based drug design, the first thing we need to do is prepare this model. This is a raw PDB file, which typically won't have any hydrogens or charges included. It may even have some missing loops. So for that reason, I'll use QuickPrep, our automated preparation wizard, the panel comprising three main sections. The first handles preparation and cleanup of the structure. Second sets tethers and restraints. The third handles refinement. Here I'll accept the defaults and I get a message at the top left of the main Mo window to give me a progress update on that calculation. Before I move on though, I'd just like to reopen QuickPrep so that I can explain what's going on in the background. The first preparation stage ensures that we've got a complete model. What we're doing here is adding in missing hydrogens, charges and side chains and building any missing loops up to 10 residues in length. Protonate 3D optimizes the ionization states of the bound molecules and their side chains, and it also generates a hydrogen bonding network through the placement of polar hydrogens. By default, we tether our atoms in the active site, and the reason that we do that is to ensure that we can retain the original geometries of those atoms as captured by crystallography. We don't want to lose those to processes such as energy minimization. Likewise, we can fix any atoms that fall outside of the active site, and we can do that for reasons of computational efficiency. And that final part of QuickPrep is the refinement stage, which performs an energy minimization to ensure that we don't have any clashes in our structure. So I see the message has gone from the top left of the main Mo window. It tells me that the calculation's complete, and for that reason I'll cancel the panel, and next I'd like to have a look at this ligand and exactly where it interacts with our receptor. So for that I'm going to hit Site View. It isolates the ligand together with any residue within 4.5 angstroms. Next I'd just like to adjust the system, so I'll go ahead and open up the system manager, pin that to the main Mo window as a means to control all of the data that we have in our system. From here I can hide and show different atom sets, make selections, render and generate surfaces. I'd like to use the system manager to control the rendering of the system, so for that I'll go to the receptor line and hide the ribbon. I'll also colour our ligand a bright colour, and with that our structure is now complete. It's modelled and ready for our fragment-based drug design. So for that, I'm going to go ahead and open up our fragment-based drug design suite. So here, these are the different operations that fall under that umbrella. Today, we're going to be using Link Multiple Fragments. So the panel opens, comprising four main sections. The first handling the system in terms of the ligand and receptor. Second controls the type of operation that we would like to perform. Here we've selected Link Multiple Fragments, but you'll notice these options are the same as what we saw in the compute menu. The third part allows for filtering, be it descriptor filters or pharmacophores. And the fourth and final section handles our refinement and scoring. I'll just move this panel to one side. Now in this example, we're going to need to simulate a case where we've got disconnected fragments bound to different parts of the pocket, and then what we can do is search for a linker to connect them in the correct orientation. Now, in our current scenario, we don't have that on the screen. We've got a single connected ligand. So what I'm going to do is go to the system manager. I'm going to right click on the ligand entry so that I can duplicate it. It's always a good idea to keep a copy of the original co-crystal structure, but this will allow me now to work on the second ligand that we see in the system manager. The original is set to inert and it's hidden from view. We're now working on the grey copy, so I'll just change that colour to make it easier to identify. And what we can do next is go ahead and delete the central core so that we can create those disconnected fragments. So I'll just raise our 2D representation of the ligand, and then I'll just delete that central portion, leaving these two disconnected fragments. I'll need to define the attachment points for these. So for that, I'm going to use the Ligand R-Vectors. So these display these green arrows in the main Mo window, which show me where I can add a substituent around the size of a methyl, but without creating a clash. So if I just navigate back to the panel, I see that now it's guiding me how to complete this operation. It's asking to select the hydrogens to mark connection points. And for that, I can use the R-Vectors that we've just added. So I'll go ahead, select one on one fragment, select the second on the other fragment. And now that I've used my Ligand R-Vectors, I can toggle those off, leaving me these two dark green arrows showing me the two attachment points. If I click on the panel, I see that information is echoed here. We've got two fragments, two connectors, and they're both essential since that's the only way to connect these two. I do just want to take a moment though to show you what would happen if I added in a third attachment point. So here, when I add a third, you see that these two turn yellow, and that tells me that these two are optional. So I can see that we've got one of them remains essential. That's the only place we can connect to the fragment on the right. But on the left fragment, we've got these two options. We could connect here, here, or perhaps even both. If I just go back to the panel and move on to the next section, looking at our filters, I find that we've got a default range of filters applied in terms of a molecular weight cutoff, a TPSA range, and a note on reactivity. However, I also notice the Check Filters button is coloured red, and I can just hover my mouse over this to raise bubble help, and it tells me the button is coloured red if ligands do not pass the descriptor filter. So to find out why they're not passing the descriptor filter, I'm just going to click on that button. It'll give me additional information at the top left of the main Mo window, and here I see that some of these values fall just outside of the default filters. So let me just manually change the TPSA range. I'm also going to choose to just push up that molecular weight slightly to increase the diversity of the ligands that we generate. Next, I'll move on to the final part of the panel, where I'm going to opt to minimize the generated structures within the receptor environment just by toggling on this option, and I'd also like to see a score written to the output database for each one of our newly generated ligands. For that, I can select between the default scoring mechanisms, but I'm going to be using GBVI-WSA today, our tried and published method. So this is in effect going to handle our newly generated ligands and write those to the output database together with a score as if they'd been docked. So with that, I'll go ahead and start the search, and behind the scenes, Mo is now searching for scaffolds that are going to link the fragments via the attachment points that we defined. To do this, Mo searches a database which contains just over 40,000 different linkers and fragments, and also Mo is creating an excluded volume around our receptor to make sure that the newly generated scaffolds are not going to clash with our receptor. The results themselves are written to a database viewer. This would be the third major window type that we use in Mo to display database entries, or in this case, database results. It looks and feels much like an Excel spreadsheet, but actually contains the 3D structure of our newly generated ligands. It would also be our launching point to various tools that we have in Mo. For example, from here we could jump into QSAR. Today, though, I'll be looking through these results to see the newly generated structures, their RMSD, together with the linkers that have been used to generate those structures. Beyond that, though, I might be keen to take advantage of the scoring function. So if I just scroll along, I should see a score here. So this is the score that we requested to be written to the output database. And now that we've generated, I see that we've generated 63 structures. So I'm just going to stop the search prematurely. And what I can do then is think about reordering or prioritizing my results so that I get the best results shown at the top. So with all database viewers in Mo, I can sort by any of the headers, these fields. So if I just right click and sort ascending, it'll ask you, sure you want to do that? Yes, I am. And now I get the best results shown at the top, bearing in mind this is an energy. So the more negative that value becomes, the better. And the score slowly drops off as we scroll down through our results. I might also be interested to examine these newly generated structures within the receptor environment. So for that, I can open up a browser so that I can see the newly generated ligands shown in green against our co-crystal fragment shown in cyan. In the browser itself, I can opt to write perhaps the score. I can select from any of the fields that you see within the database viewer. So I'll be using the score so that it's displayed here within the browser as well as at the top left of the main Mo window. And with that, I can click to just cycle through and have a look at some of these newly generated structures. So that's how we link multiple fragments and to leverage a fragment screen. Today we've been using the Link Multiple Fragments operation to link two separate fragments that occupy different parts of a pocket and then find a suitable linker to create a single small molecule ligand. We also minimized and scored our newly generated structures in the receptor environment. I hope that you've learned a lot today. If you have any questions, please do reach out to me at support@chemcomp.com.